Hello everybody, first of all thanks to the organizers team to let me talk to you about my side project written in Go, and obviously thanks to all of you who are listening me. Before diving into the subject, let me introduce myself and make my self-promotion to you. My name is Sylvain Combraque, I'm from Paris in France, so sorry for my baguette accent, but I'll try my best to speak as well as possible. I'm traffic contributor. I'm also the creator of the cache system we'll talk about. I'm the cache handler Caddies module maintainer, and I'm an active open source contributor. And you can find me on GitHub searching Darkweek and Darkweek Dev on Twitter. So let's replace the context of why I started to dev using Golang and how I came to do it. As I said, I'm traffic user since version 1.4. I'm contributor and helper. Then for those who don't know traffic solution yet, it's a reverse proxy created to manage container architectures and its container first approach. It supports the hot detection deployment, the scaling. It load balances your request automatically using the weighted round robin strategy, and it uses only a specific port for all protocols. So traffic manage for you the service resolution depending a host and a CIGR in entry with a path or many other cases, many other conditions. Then it's the pivot point of your infrastructure. It's like Kong or Nginx for those who have already worked with them. But it's really simpler to configure and to set up traffic instead of Nginx or Kong. And it consumes less resources. So it's the best choice. Another good point is the fact you can install it on your development environment and continue your work instead of bigger reverse proxy. Then, as you can hear me, I love to use traffic, but after months to use this solution, there was an issue I was facing too. There wasn't any cache system internally to traffic, and I talk about the traffic community edition, but because there is a cache system in the enterprise edition, but I can't pay for an enterprise edition, so I'm using only the community edition. Then all requests would have to resolve the cited service, so it instantiate the TCP connection, it resolved the DNS, etc. And it took many milliseconds to be done. So we can say, okay, 2 milliseconds is nothing, but 2 milliseconds per request. So if you have 100 requests, it will take 2 seconds. I searched after a cache system solution, but nothing appeared to be as efficient as I wanted, or it was only POC. So after many nights to spend to look after that, I decided to create my first program in Go. That will be a cache system. The fact I was totally a beginner with this language, so I learned from scratch using a real project, and it's better to learn a language with a real project instead of tutorial, because you invest more time to learn the best practices, etc. So this project called Soin is actually in version 1.6.19. The fun fact, the release names are free beer names because I love to drink beers and I love open source and free. So let me show you how Swan is versus Varnish. Obviously, this image is just a troll. I love the Varnish developer team, but I don't like some parts of the Varnish tool. So I think a demo is better than words. So let me show you how to set up Swan with the minimal version. First, let's see together what's in the docker compose.yaml file. We are declaring some services, traffic, that's the reverse proxy, whoami, which is a container that will give us some information about the container that handles the request, and it will print the headers and will respond to the domain.com CIDR. After that, we declare the Swan service. It will be placed before the reverse proxy and will handle all incoming requests. And we map the Swan configuration YAML file to be to the path configuration /configuration.yaml. And the configuration file looks like this. As you can see, there is no tricky part in the minimal configuration. We declare the port to listen in the default cache port key, and we tell to cache the response for 10 seconds. As its time declaration, it could be 10M for 10 minutes, for example. After this, we will launch the containers, and the first call will be around 14 milliseconds after the first warm-up from traffic. And once the response is cached, and it responds under 3 milliseconds. You can note that I was recording, so performances were lower than the production, and I'm under macOS OS, so it's not the best OS to run programs, some performance programs. And as you can see, that cached status and hash headers are present when it's served by Swan. So after this demo, let's dive together in the theory of how to build fast application using Go and what were the complicated parts. First, I can't talk about Golang features without mentioning the Go features. If you don't know that, a Go routine is basically a part of a thread which will run one task, one function detached from the main thread, and will close if the main thread stops or if it reached the end of the function, of the Go routine function. So, in this example, we can see that a cost function will be delegated to another thread to be more efficient, and because we don't need the result of this execution, then here the update cache eventually method is really cost effective due to headers validations, RFC checks, etc., and many other conditions. And you can easily do concurrency with the Go keyword placed before function declaration and before function usage. Then another big feature is the channels. We can wait in the main thread for informations or push data to the Go routine. And today, a real Golang application without channels and obviously Go routines doesn't exist, or it's really rare, or it's very little application. There is no more a lot of code. And a channel is like a bridge between the thread that instantiates the channel and the associated Go routine. So you can instantiate the Go routine from another Go routine. And the main thread for the thread will be the instantiator and not the instantiated Go routine. For example, here I set a timeout to the current request and run a Go routine function that will determine if the request must be coalesced or just passed to the next middleware. and we send an error that can be nil in the error backend channel. So we wait for the fastest one between the request context done event, that means the request process finished, and the error backend channel. If the fastest one is the request context, we switch between cases to know if that's a timeout or not. And if it's a timeout, you'll receive a gateway timeout response. And if it's a timeout exceeded, deadline exceeded, so you'll receive a gateway timeout response with its associated status code. So it's a 500 true. And if the fastest one is the error backend channel, we just send the response to the client and return the channel error. Then I was facing an issue that Go didn't support generic types at the moment I started the project. So we had to find some tricks to be able to pass as possible a generic object. The solution is to apply the dependency inversion principle to decoupling software modules, thanks to Wikipedia for that, and use interface instead of the implementation. So it's a little bit tricky to implement an interface, and sometimes you can implement an interface under the hood without knowing you're implementing it. So in Sylvain, we have some providers to be able to let the user decide which kind of storage system should be used, depending the match URL or depending the KDE's route, for example. Here we are defining the type of each provider, and each provider define the same function. So there are list keys, get, set, delete, init, and in the latest release of Sylvain, we have the reset method. So these methods have the same signature, and to make a generic object, we can define an interface like the abstract provider interface, which will contain the method signatures, and each structure defining all the functions with the same signatures will considered as implementing the interface and can be part of an abstract provider interface array, for example. And after that, we can pass our all week and our badger provider, and as the two structures are implementing the interface, it won't crash, but in your IDE you'll have auto completion for only the abstract provider interface and not your real objects. For example, if your object define a specific property, you can't access directly the property, but you can cast your interface into your real implementation. But Golang casting is really slow and really CPU consuming. So this is now outdated with the introduction of the generics since Go 1.18, but we keep the interface to be compatible with the other systems that are built in lower version. So for example, Tyke is using Go 1.15, so we can't use it. We can't use the generic types. So there are many other cool features in Sylvain, and the first one, compared to Varnish, that's a really simpler configuration. It's really simpler than the VCL for Varnish configuration language. And here you just have to define a YAML file and it works like a charm. On the left, you can find the minimal configuration to be able to run a standalone Swan instance. That means Swan will be run as a proxy, and on the other side, you have a more complex configuration, with headers to be added to the cache key, a regex to exclude to be cached. For example, you can define the TTL. You can define the SSL providers and many other things. And then, as it's YAML, you can use anchors. You can write scripts to create dynamically the configuration, and the most of all, the configuration supports the hot reload in the standalone version. Then you don't have to restart Swan if you change the configuration. But I plan to disable by default this feature in the future to avoid memory leaks, and because it makes side go routine running to listen the file changes and reload the configuration when the file is saved. Then keep in mind that existing keys are always stored when you and available in your providers, and will be purged only when the TTL reach 0, or if you decide to purge the cache by regex or URL or tag based or anything else. But we will talk about that later. And it will happen each time you reload the configuration. So as traffic, Swan is a container first designed to be compatible with as much as possible with existing systems. You can define a docker compose.yaml file for Swan, exposing the needed ports, and map the configuration file to the configuration file path inside the container, and be sure the reverse proxy is in the same network than the Swan instance to avoid the external requests on your network. So this is the configuration for working with Swan out of the box. But there are two ways to add this HTTP cache to your project. The first one is a standalone version and set Swan as a cache proxy, but it's the pain way because you'll have to maintain the Swan instance in your stack, detect if it crashes, and it's really hard and a pain for DevOps. So that's not the recommended way. The second one is the middleware integration. What's a middleware? Middleware is just a layer placed before your application that run code to format a request, for example, or wait limit, or can just log the incoming request and outgoing responses. In Golang, middleware is just an HTTP handler or an handler func that takes the request and the response as parameter, and in some integration cases it can take more parameters, like the next middleware to call. So we prefer this method because you can already have a traffic or a caddy as a reverse proxy or anything else that makes a bottleneck in front of your apps. And Swan is well integrated in some proxies or API management, like caddy, traffic tag, roadrunner, and many other ones. So, for example, here I implemented the server HTTP interface. That's the caddy handler interface, and the first parameter is the response writer, the second one is the request, and the third is the next handler to call. And here I'm just I override the request context with the setBase context. That's an internal method in Sylvain. So I define a new writer, and after that I'm just overriding the context, and I return nil. But there are other part of the code that's not the full server HTTP code in the KG module, because the original one is really long. But we can handle with the custom writer the write inner, or we can rewrite each method defined by the HTTP response writer. And for example, we can just keep the response for us until it reached the end of the response body, and only after that return the response body. Okay, for that. And another cool feature is the support for the request coalescing. That means when you get multiple requests at once on the same route with the same context, you'll temporize all incoming requests, and you'll request only once your backend, then use the same response for all temporized requests. That's pretty cool, because your backend service can be on a cheaper server, or like Raspberry Pi, and your cache system will be on a bigger server in data center or any other stack. And couldn't handle all requests if it was on frontline. So imagine you run a PHP application like a WordPress, and it makes 800 call to the 800 connections to your database, and process many templates, and it render some PHP into HTML. It's really CPU consuming and time consuming, because 800 connections to the database would be 800 TCP connections. So thanks to SingleFlight for providing a library that can be used to handle and coalesce requests easily. So recode a new coalescing system would be really hard and really time consuming to maintain. So another feature is the new cache status HTTP response header support, and the age response header. With this, you know how many seconds left before the key will be purged, and since how much seconds this response is stored. Not in this example, it missed the TTL directive in the cache status header after the hit. Okay, and as Swing takes care of users and won't let them manage the cache through an API, it provides some endpoints and secures them with authentication. At the moment, you can only list keys to avoid content leaking, and purge cache for a resource, or multiple by regex, or multiple by tag. So let's see together how it works, and how I did to make it as faster as possible without impacting the base cache system. So first, the configuration about all the API endpoints are the following. You have to define the API block in the YAML configuration file. Then you can override the main base path, which is the Sylvain API by default. At the moment, Swing supports only 3 APIs, but in the future, it could support more endpoints. For each endpoint, you can override the bath path, tell if it's enabled or not. It's false by default. Then specifically for the security endpoint, you are allowed to define a secret and a list of users to be able to log in as these users. For the Swing endpoint, you can tell that you want to protect related routes behind JWT security firewall. And for the cache management, the default bus path is Swing, and you can send a GET request on the base endpoint to list stored keys, a GET request on the /surrogate keys to list all tags stored with its cache keys associated. You can send a purge request on an ID or a regex to purge it, and you can also send a purge request on the cache bus path with the header surrogate key to purge the cache by tag. Note that the tag group 1 or more cache keys to invalidate, and you can send also a purge request on the flush endpoint to flush the whole cache storages and the surrogate storage. So here are some examples about the results when you are sending requests on this endpoint. As you can see, the bus path route returns an array containing all keys stored. In the I miss my words. All keys stored in the provider, and the purge regex path return nothing. So, as I said, Swing provides the JWT authentication using JWT token, and you can log in on the login endpoint, sending a post request on a JSON content type header and a JSON body containing the username and password. Then you can refresh your token, sending a simple post request with a JSON content type header and a cookie Swing authorization token, which contains the JWT token in it. So here you can tell you in your mind, okay, it sounds good, great, perfect, blah blah blah. But I want to know how to code that. So the magic under the carpet is basically I get the main bus path from the configuration. If it doesn't exist, it will use the default value Swing API. Then after that, I load each endpoint using the initialize function, which takes a provider and a configuration as parameters. If the endpoint is marked as enabled, I just create an HTTP handle function with and without the trailing slash on each endpoint, and have a property named handle request. As the name specify, to handle the incoming request. Then the path is built from the concatenation of the main bus path and the endpoint bus path. This code is running at the Swing startup, and it's only when it's running, and it takes only some milliseconds to be executed. So Swing is compatible as middleware, HTTP filter, or plugin with some many Golang softwares, and it works with the standalone mode with Apache and Nginx. So it was really funny to dev this, but I was facing the most complex part. The first one was the RFC implementation and support. An RFC rule is really good to face and fight the depression because you think you're done with that, but another rule comes, or an update, or anything else. Or someone say, I don't want to do that this way, but this other way would be better, and that's a pain. And you have to rewrite, obviously, some part of your code to respect the RFC. Because an RFC is the standard of the web. The RFC for request for comments designs the semantic of the web and applications to homogenize and define standards of your responses, driving your application behavior, and don't let the creator of the tool be free about the implementation, the logical part, and the data process. So here is an example with the RFC 7234. That's the first page, and there are 42 another pages. That was really a pain to support that, but thanks to other developers that implemented it in the past, then I can take advantage of the existing work. So when you're implementing an RFC, you realize that just if-else conditions, and you can see in this example, to manage the cache control header, it's just a condition after others to be able to test every cases. And that's the same thing for the expires, either to check if it had already expired or always good to be served, for example. After this very long technical part, we can now talk about the deployment system to have the full workflow. The development is secured by the GitHub Actions to run linter, unit test, end-to-end tests, and deploy only tagged version on master. First, the linter and the unit tests are running, so it just installs the Go environment, Golang CI lint, and runs the Golang CI lint to ensure the code is well linted, and the Go test command inside the container, because some test cases need to talk with an external services. Once the linter and the unit test are green, we run the plugin workflow. Workflow that ensure every middleware integrations are building well and returns the expected headers in the HTTP response. So for that, it runs the services inside Docker and loads one inside that as a middleware with a given configuration, and after that it runs Newman to run Postman collection in an headless mode. So here, if everything is green, we can now tag our new version on the master branch. That will trigger the release workflow. It will deploy the traffic with Swan middleware built in, and the Swan itself Docker images to the Docker hub, and runs the Go releaser to tag the new version and be able to use it as a Golang dependency in our projects. And just to note, the Go releaser take around between 10 and 30 minutes to index your new version. So it's based on the .goreleaser.yaml file, either at the project directory specified or the root project otherwise. And here we build for each environment on each available architectures. Then every test and deployments are done, and we are all happy, and we can communicate on social networks that there is a new version. So for those who want to see what is the power and performances of Swing, here are some metrics to view how many requests it can handle per second. It took around 35 seconds to serve each 101,000 requests. And the max response time was 56 milliseconds, and the minimum one was 0. It took around some microseconds, but rounded to 0 milliseconds. And it's due to Badger power in combination with the asynchronous updates. So what's next in Swing? We plan to stream each response body and support the ESI tags. The ESI tags allows the developer to include parts of the body to be requested by the proxy, the cache system, or the proxy like Cloudflare and other ones, and replace the ESI tag with its content response. So enhance the performances and make some WordPress and PrestaShop integrations, so make it better to be able to deploy easier Swing in front of them. And I plan to release a new stable version on this week. Not really sure about the date, but I will try. And obviously, if you want to contribute, you're welcome, or open an issue, or just say, oh, wow, it's awesome. And to finish this talk, I just want to say thank you again to the ContainerDays organizers. Thank you to all of you for listening me. And don't be shy, you can ask me whatever you want. I'll try my best to answer it. Anyway, I'm available on Twitter if you have some questions. And like Gordon Ramsay is saying, thank you.